Welcome viewers. In today's lecture of information technology and its application in business, we start with logic. Now, what is logic? We say that logic is fundamentally formal method of reasoning. That means, for happening or not happening of an event with given reasons, if we state all the reasons, then we say it is logic. Now, let us move. We define logic as logic is formal method of reasoning. Let us understand with an example. Suppose we are given with a statement that if it rains and I have an umbrella, then I will go for a walk. That means, if I am walking, that means under this circumstance of given statement, I have to have two reasons. First is it should rain and I should have umbrella. So, we say that if it rains and I am having an umbrella, then I will go for a walk. Now, under this purview, we say that there can be four outcomes of this logic. We say that if I am walking means there is a rain and I am having an umbrella. But if someone says that I am not walking but I am sitting somewhere, then there can be three reasons under given statement. The first reason is it is not raining and I am not having an umbrella. The second reason is it is not raining but I am having an umbrella. The third reason is it is raining but I am not having an umbrella. So, here we consider that given circumstances I have an outcome, then we consider that this is nothing but a logic representation. So, we say that if in a logic we define all the possible reasons for an outcome, then we say it is termed to as truth table, or in other words, a tabulated representation of all the possible reasons and the given outcome specified in logical form, that is a statement, is termed to as a truth table. So, now we are very clear what is logic. We say that given a statement, if we give reasons for the outcome, where the outcome may happen or the outcome may not happen, then the set of all reasons is termed to as logic. Now, let us move to certain terminology of logic. The first is Boolean variable. We consider that a symbol which can attain multiple values is termed to as a variable. Now, Boolean variable is nothing but a symbol which can attain two values, either 0 or 1. That means, a Boolean variable can take only two values. Now, second is Boolean constant. We say that a symbol whose given value does not change until and unless it is changed programmatically, then it is termed to as a constant. So, again there are two Boolean constant, one is 0 and second is 1. That means, if I say x is a variable, then x can have two values 0 or 1. If I say x equal to 1, then x becomes a constant. The third is logical operator. We say that given a logical statement, if we join or if we connect them by certain logical manipulations, then we say it is called as logic operator. For example, the statement if it rains and I have an umbrella, then we say and is nothing but a logical connective, or it is also termed to as logical operator. Now, we formally define that logical operator is nothing but an operation which is carried over binary variables and binary constants, or over the group of binary variables and binary constants. Now, let us understand what is formal logic. We say that in formal logic, a statement, also termed to as preposition, is a declarative sentence which is either true, that is 1, or false, that is 0. It is easier to communicate with computers using formal logic. That means, we say that computer is a binary machine which can understand only two values, that is 0 or 1. Suppose we want to compute certain statements, then for the statements we define them in a formal logic form where the statement output will be either 0 or 1, or in other words true or false. Then we say it is nothing but formal representation of statement in logical form. Now what is a Boolean function? We say that a mapping of Boolean variable to a Boolean value is nothing but a Boolean function. That means if I say I am having certain set of inputs, then with respect to inputs, if I define certain connectives, that is logical connective between them, then the outcome of that particular equation is nothing but a Boolean function. Now what is a logic diagram? We say that all the logic can be represented by certain symbols, typically termed to as gates. Then we say that a gate or a graphical representation of logic is nothing but a logic diagram, or we say composed of graphic symbols for logic gates, a simple circuit sketch that represents inputs and outputs of Boolean function is nothing but a logic diagram. Now let us understand fundamental logic. There are three fundamental logic to understand. The first is termed to as AND logic, the second is termed to as OR logic, and third is termed to as NOT or negation logic. Let us first understand AND logic. We say that AND is represented by a dot notation in computers, and we say it states that the outcome is true if and only if all the given reasons are true. That means if I define a statement in which I have an outcome, then we say the outcome will be true if all the given inputs are true. For example, if I say if it rains and I am having an umbrella, then I will go for a walk. That means to go for a walk we have to have rain and we have to have umbrella. But let us talk of the second logic, that is the OR logic, which is represented by plus sign in computers, and we say the outcome is true if any one of the given reason is true. That means if I say if it rains or I have an umbrella, then I will go for a walk. That means if it is raining, I will go for a walk. If I have an umbrella but it is not raining, then still I will go for a walk. And if either of them is true, we say yes, I will go for a walk. That means I will not go for walk if neither I am having umbrella nor it is raining. So we say it is termed to as OR logic. Now the third logic is termed as NOT logic or negation logic. Negation is nothing but inversion of the inputs. It says that if the input happens, the output doesn't happen. If the input doesn't happens, then the output happens. So we say that the outcome is true if the given reason is false. In computers it is represented by many symbols, that is by placing a bar over the variable, or by placing a quotation mark after the variable, or placing a tilde character before the variable. So these are three fundamental representation of NOT logic. Let us move to logical operators. So now we say, since we have defined three logic values, one is AND, second is OR, third is NOT, then let us define their operations over the binary variables 0 and 1. So we say that in AND operation, if 0.0, that is, this is the AND operator dot, so 0.0 is 0, 0.1 is 0, 1.0 is 0, and 1.1 is 1. That means the output will be 1 if and only if both the inputs are 1. Now moving to OR, we say that 0 plus 0, keep this thing in mind, this plus is not arithmetic addition, it is a logical operator. So 0 plus 0 is 0, 1 plus 0 is 1, and 1 plus 1 is 1. That means the outcome is 1 if any one of the input is 1. The outcome will be 0 if and only if both the incomings are 0. Now let us move to the NOT or negation logic. Negation logic says that if 0 is complemented, it becomes 1. If 1 is complemented, it becomes 0, or in other words, if the input is 0, the output is 1. If the input is 1, the output is 0. Now, let us move to logic representation. Fundamentally, there are 6 representations that exist to represent a logical value or a logical outcome. They can be in classical form represented by true and false. The second form is Boolean, that is also called as binary representation. It is 0 and 1. If we consider switching logic, then it is represented by on and off. The level logic is represented by high and low. The voltage logic is represented by plus 5 volt and 0 volt, and the response logic is represented by yes and no. That means we can have 6 representation of a logical statements, where one thing we have to keep in mind that if we are representing in level, then all the representations must be high and low. We should not mix that high and false or true and low. That means intermixing should not be done, although they carry similar meaning. That means if I say true, it is 1, it is on, it is high, it is plus 5 volt and it is yes. If I say false, it is 0, it is off, it is low, it is 0 volt or it is low. So, these are nothing but the representations used in various formats or for various purposes in a computer system. Now, let us understand the basic logic or classical logic. Now, classical logic says and the outcome is true if and only if the given reasons are true. The OR logic says the outcome is true if any one of the given reason is true, and the negation says that the outcome is true if the given reason is false. Now, let us understand the AND logic with reference to an electronic circuit. Here we consider that we are having a battery, we are having 2 switches in series and we are having a bulb Z. Here we define that logic 1 is nothing but switch closed, logic 0 is nothing but switched open, and for the output Z we define that logic 1 is there if the light is on and logic 0 is there if the light is off. Now, with reference to this circuit, we can clearly understand if we close A, nothing happens, but if we keep A closed and we close B, then and only then this bulb will glow. So, from this table we find that if switch A is off and switch B is off, the bulb is off. If switch A is off but B is on, then still the bulb is off. If switch A is on but B is off, then still the bulb is off. If A is on and B is on, then the bulb is on. That means AND logic is nothing but switches in series. That means the outcome will be true if and only if the inputs are true. Now, every logic has 2 basic definitions. One is for outcome true and second is for outcome false. Let us define for AND gate. The first definition says the bulb Z is on if switch A is on and switch B is on. The second definition says the bulb Z is off if switch A is off or switch B is off or both switch are off. That means we have to note one very important thing: what we consider as true in AND becomes negative in OR. This is one of the reasons that the AND and OR logic are termed to as complementary logics. Let us move to OR logic. In OR logic, we say that the circuit is described in form of parallel switches. That means here we say if any one of the switch is on, the bulb will glow. Let us understand by the truth table. We say that if switch A is off and switch B is off, the bulb Z is off. But if switch A is off and the switch B is on, that means the circuit will get path from this side, the bulb will be on. Again, if switch A is on and B is off, then the circuit will complete to this path, the bulb will grow. If both the switches are on, then the circuit is completed by both the path, and the bulb will glow. That means the bulb will glow if any one of the switch is on. So let us understand the two definitions, the first for positive, that is true value, and the second for negative, that is the false value. We say that the bulb Z is on if switch A is on or switch B is on. The second definition says the bulb Z is off if switch A is off and switch B is off. So now we can have a correlation between and or logic, that whatever is true in and becomes false in or whatever true is in or becomes false in and. Now let us move to not logic. In this case we connect the switch in parallel of the bulb. That means if the switch is off, the bulb is on. If the switch is on, the path gets short circuited and the bulb is off. So from the truth table we say if the switch is off, the bulb is on. If the switch is on, the bulb is off. It is nothing but invert or negation logic. Now let us define logic gates. We say that in a computer system we are having electronic circuits that performs their output over the logical connectives applied over the input, then they are termed to as logic gate. Or in other words we say that logic gates are nothing but electronic circuits whose output is a logical function of inputs. So let us define that an electronic circuit whose outcome is logical function of the given input, it is termed to as a logic gate. So we say that this is a logical circuit which can have more than one finite inputs, and usually it has only one output, where the output is nothing but a logical function applied over the input. So mathematically we say output is nothing but a logical function applied over input is a gate. Let us understand the categories of gates. We say that the logic gates can be categorized into three major categories. First as basic gates, the second as universal gates, and third as exclusive gates. The basic gates comprises of AND gate, OR gate and NOT gate. The universal gates comprises of NAND gate and NOR gate, and the exclusive gates comprises of XOR gate and XNOR gate. So in turn there are 7 logic gates that exist in computer system, with reference to which all the computations or all the circuits are developed. Now let us understand what is AND gate. We say that this is the standard symbol of a AND gate. In this figure we have shown only 2 inputs, but remember that a AND gate can have minimum of 2 inputs and maximally it can have some finite number of n inputs, and there is only one output. Then we say there are 2 definitions of AND gate. The first is the output Z is true if A is true and B is true. That means the inputs A and B both must be true for output Z to be true. Then the second definition says the output Z is false if A is false or B is false or both are false. That means a AND gate follows all the rules of AND logic what we have studied earlier. Let us move to OR gate. This is the logical symbol of OR gate, where we say in this symbol we are having 2 inputs shown, but there can be more than 2 inputs. That means a OR gate can also have 2 or more finite inputs but only one output, where the output is nothing but a operation or applied over all the inputs. So we say again the definition of OR gate is similar to that of OR logic, where the output Z is true if A is true or B is true or both are true. The second definition says the output Z is false if A is false and B is false, also depicted by the truth table. Let us move to the third basic logic, the NOT logic. It also follows negation logic. This is the symbol of NOT gate. One thing here again we have to note that a NOT gate has only one input and only one output, where the output is complement of input. Here again we have to note one important thing, that the negation is represented by a circle that is also termed to as a bubble. Then the definition says the output Z is true if A is false, the output Z is false if A is true. Also from the truth table we can find the same thing. Let us move to universal gates. Now let us define what are universal gates. The definition of universal gate is the gates which are derived from basic gates, that means they are derived from AND or AND NOT, and do possess a capability that all the other gates can be derived from them. That means if I define a gate to be a universal gate, then there are two properties of it. First, it is derived from basic gates only, and second is from the universal gate you can derive all the other remaining 6 gates. We say the basic gates are AND or AND NOT. So there are two universal gates which can be formed. One is NAND, that is also termed as NOT of AND, and second is NOR, also termed as NOT of OR. That means by these two gates NAND and NOR we can define all the other gates, or in other words we can say, if you are given with only NAND gates you can build a complete computer system, or if you are given with only NOR gates then you can build a complete computer system without requiring any other gate, because all the gates can be derived by these gates. Let us understand in a detail. We say that a NAND gate is NOT of AND. So we consider that the AND gate is followed by a NOT gate. So here we say A, B are input, then the output here becomes A dot B. Since we have a NOT gate, we simply invert the values, so it is A dot B bar. This is the equation of NAND gate. Now this circuit can be reduced by removing this connection as well as this triangle, also called as buffer. So we say that these two geometric symbols are removed and the bubble comes to the AND gate. So this becomes a NAND gate. Again we have to note one important thing, that a NAND gate has minimum of 2 inputs and the maximum number inputs can be some finite value, and it has only one output. Now we say again the two definitions of NAND gates are, the output Z is true if A is false or B is false or both are false. Then the second definition says the output Z is false if A is true and B is true. That means from the truth table we say if 0 and 0 is 0, then in NAND it becomes 1. If 0 dot 1 is 0, then in NAND it becomes 1. Similarly 1 dot 0 in NAND produces 1 and 1 dot 1 bar produces a 0. That means a NAND table is just complement of AND table. That means we replace all the output zeros by ones and vice versa. Now let us move to NOR gate, which is nothing but negation of OR. Here we say in symbol the OR gate is followed by a NOT gate. So we say here the equation becomes A plus B and the output becomes A plus B bar, that is the complement of OR. Again we say we reduce this geometric symbol, that means we remove this buffer and this line and we move the bubble to the output of OR gate. So this becomes the logical symbol of NOR gate. Again note that a NOR gate has minimum 2 inputs and maximum n finite inputs and one output. The definition of NOR gate is the output Z is true if A is false and B is false. That means if both the inputs are false, then the output is true, and the output is false if A is true or B is true or both are true. That means from this table we can find that this is nothing but the negation of OR. That means OR comprises of 1, 1 and 1 here and 0 here, and NOR comprises of only 1 here and 0 at all the 3 places. In this lecture, we have studied about logic, the definition of logic, then what are the fundamental logic, that is and, or, and not. Then we have understood that how the logic can be converted into electronic circuits called as gates. Then we have classified the gates into three categories: the basic gates, the universal gates, and the exclusive gates. Then we have studied AND gate, OR gate, and NOT gate. Then we have also studied that the NAND and NOR, the universal gates, are nothing but the gates which are derived from AND, OR, and NOT. They are also called as negation of AND, that is NAND, and negation of OR, that is NOR. Hope you have enjoyed this lecture.